Okay, we're back for video 2 of lecture 2. We're going to talk briefly about, kind of go back to this global map and compare and contrast again, and then we'll dive into climate change and move on from there. So, top energy producers in the world. Do you think you could name them?
United States, Middle
Saudi
East,
Arabia.
and Asia.
The Middle East isn't a country, neither is Asia. But the U.S.
I'm just going by the chart.
U.S., Russia, Saudi.
It's in the book.
Russia, Saudi Arabia.
Venezuela. China.
All right. So I think everyone's identified the U.S.
Yeah.
There's some question about Russia.
That's kind of dark.
Saudi Arabia
Actually, in Europe in there too.
for production. This is consumption.
Consumption.
Okay.
So it's not
Correlating with this map.
not correlated to this map. No.
But Brazil and Venezuela produce pretty.
Yeah, I think we're talking about per capita
Oh. What kind of production are we talking about?
consumption, total energy consumption.
Consumption,
Mm-hmm.
United States is the highest.
Okay.
Yeah, they are the highest in consumption by far. Europe
All of Europe.
is in there, and actually the Middle East is in there too.
Okay. We are doing individual countries though, so I'll start with the
That's
top.
Saudi Arabia.
Yeah, this is Saudi Arabia, but this is the Middle East.
Yeah.
The top is actually China. They surpassed us in the mid-2000s in terms of energy consumption.
How would you just say that we were the highest? Like, just talk about this last time.
He's not talking about per capita.
Oh, okay.
Yeah, different quantities.
Okay.
Yeah.
Now.
So China produces almost a fifth of all the world energy, and then consumes a little bit more than that. The U.S. not far behind. We consume about the same amount, but we produce a little bit less. So remember these kind of production-consumption relationships. You want one to be high, and the other to be a little bit lower. Russia, number 3. And then number 4 is India, recently. And then the last one, someone named it earlier, I was impressed, Japan. So remember those RPR, reserve to production? So if you look at Japan, low reserves would correlate to low production in this case. Japan has the lowest RPR of these top consumers. So remember I described Korea as having kind of a lot of consumption, but they have none of their own resources. Japan's the same way. They don't have much or any in the way of coal, gas, and oil. So economically, that region, even though it's fairly advanced and technologically very advanced and economically stable, its fuel dependence can be problematic. When fuel prices change, Japan and Korea kind of suffer for it. So Japan...
Russia's actually doing the best.
Yeah. Yeah. So Russia, it's a fun kind of geopolitical situation, because where does Europe get its gas? From Russia. And so anytime Russia needs to hold sway over Europe, which they do, well, I mean, Europe fights back with their own sanctions. You know, it's a constant balancing act, I guess. But
When they do it when winter's coming.
yeah. Oh, yeah. You can watch the Russian gas prices change with the seasons, change with the political climate of the area. But so my next question then, given that, I mean, we know energy and climate change are linked. That came up on day 1. Looking at this map, or based on other information you have, where would you put your attention for addressing climate change? Mitigation.
Someplace good, United States.
Okay, U.S.
Well, let's say
Someplace you can.
the
I can't
world
change
leaders.
things, you know.
What were you about to say?
I'd say the world leaders in energy consumption have a responsibility being those that getting into the same trends on the right path,
Okay.
right track. I don't know. Instead of having such a rivalry with one another, we could learn a lot from Russia about us. It's just in regards to our culture and what we believe. Also, the religion has a lot to do with it, but I think, what's your name in the red shirt right there?
Type.
Didn't you mention something about how there's so much emphasis on individuality? People are always worried about themselves and they're so self-centered. Worried about the world around us so much. But yeah, you summed it up soon as that. Yeah, what I was just trying to get at is that if we are the ones that are on the top, we should try and, I suppose, represent that position with a little more intent.
I would suggest a different alternative. I would put my investment in India. As a country that is developing with such an enormous population and yet still so small, as they develop it, they develop in the right way. That ratio, by the time they are up there around 20% consumption, their production could be much higher if the resources are available in the country, which they are.
So you're aiming more at kind of responsibility in past emissions. You're aimed more at kind of responsibility for future emissions. We're not going to dive into it just because you could write a PhD dissertation on any one sentence that any of you just uttered, and people have and do. But it's a great question. This is the debate that drives the UNFCCC negotiations. Paris, last year, who's responsible? Who is responsible? Should we worry more about the U.S. and Europe that have historically driven all climate change? Or should we worry more about, remember that 1/3 from day one? 1/3 population that has no access to electricity? Should we worry about that? If they develop the same way we did, as you just brought up.
Yeah, it was funny. I was in my intro to business class on Monday before I came here, and there was a guy who's open arms about corporations and how he loves them. He's a corporate lawyer, so he's talking about how a corporation spreads the liability out so that people who buy into the corporation wouldn't be held liable for what the corporation does. So it shifts the responsibility off to a faceless entity. Nobody can take responsibility. And that's probably one of the biggest problems we have in the world is these greedy corporations that slough off liability and responsibility onto basically nothing.
Yeah, that's a pretty common sentiment.
It's fine, and we feed into it just as much as they feed back to us. So,
You can't make personal choices there.
indeed.
Probably societal level.
But a lot of choices are made for us, depending on what's available.
All right. So with that in mind, because you always have to be thinking about what caused this, where do we go with this? It's not just technology, it's society. Let's kind of go techie for a minute, or half an hour. Climate change. Someone give me a description. What does that even mean?
It's climate change.
Interesting.
What are you going to say, man?
Yeah, it's kind of put in more words.
Based on what we've already seen, as like temperature trends and weather patterns, things like that, just seeing that there's major change and rapid change in not only our weather and our temperature locally, but also just the composition of the atmosphere based on, like carbon emissions, things like that. So I think that global warming and climate change are a little different, but they're definitely very interlinked because, climate is basically has everything to do with temperature, weather, and so we're seeing extreme temperature, extreme weather on both ends of the spectrum, in places we haven't yet. So.
Okay, you brought up two things that I think perfectly introduce this. So obviously changes to atmospheric composition. This is the crux of the issue. And we'll talk about that in a minute. The other thing you brought up is weather. And we need to be careful about how we use that word. What does weather mean to you? Temperature
change.
Short
Yeah.
term.
Short
But
term.
that happens regardless of what we do.
Yeah, weather is weather.
I mean, we're gonna have a climate change no matter what we do.
Well,
You're gonna have that change. It's gonna always exist. It always has, and it always will.
Yeah.
Before we were on Earth, and after we're gone.
right. So that's what I want to get into. And we'll start with the difference between what you just said, climate and weather. They are two very different things. So
Short term weather, long term climate.
yeah, weather, this is an order of days to weeks. You know, we say it's cold, it's rainy, it's sunny, dry. That's weather. Climate, we're talking years to decades. So whether it's rainy today or sunny today does not depend on climate. It's just its own. So one of the big controversies, at least in the political realm, is that politicians and people who are in charge of this whole thing don't seem to understand the difference between climate change and weather. So does everyone remember Senator Inhofe from Oklahoma came into the Senate chambers? Keep in mind, this is the Senate chambers, one of the most revered and powerful legislative bodies on the planet. And he came in, if I can find it, with a snowball on a winter day to prove that global warming was a hoax.
Oh my gosh.
He's a senator, the senior senator from
Oh
Oklahoma.
my
They've
God.
done stupid things.
Yeah, for sure. But this is a classic example of the difference between weather and climate.
Mhm.
Yeah, it's snowing because it's winter. Climate change has nothing to do with whether it's snowing that day. So I just want to make sure we're not confusing those two words right now. So let's go back to this. Changes to atmospheric composition. And we'll get back to what you were saying in terms of like natural climate change and global cycles and things like that. Do that. What is the change to our atmospheric composition that you brought?
Yeah. Carbon dioxide.
Okay, so you're specifically bringing up carbon. It's not just carbon.
What about
Methane.
wars and stuff like that? When they let off thousands and thousands of bombs and missiles, doesn't that have a little bit of effect in here?
Okay, well, yeah, we'll talk about that in just a second. Yeah, so it's more than, we haven't said where these emissions are coming from. Just said those are the changes. So you're doing carbon dioxide, methane. This is what we're talking about for changes to atmospheric composition. What else?
Position of the globe.
Oh, we're just talking about atmospheric composition, right?
Water vapor.
Water vapor, which can have a cooling or warming effect depending on where it is.
Well, isn't the atmosphere only like 10 miles thick anyway?
It's tiny.
Yeah.
Itty bitty. Yeah, it's not a thick.
From less.
We're a very thin
low.
show. Yeah. Anyone know any other emissions that contribute?
I'm sure all butane, all the other.
Well, there's a great level of acidity that's coming up the Pacific Ocean based on issue.
That's a completely different issue.
Oh, yes.
That's localized in the short term, and it's from a point source. So this, we're talking about global changes to composition, just from everywhere.
Well,
Nitrogen,
lower
hydrogen,
oxygen levels too.
oxygen.
So what?
Are there lower oxygen levels too?
Lower oxygen percentage,
Yeah.
but not levels. Not in like a big way. So as you put more stuff into the atmosphere, even if the oxygen content stays the same, it's just a smaller proportion of the atmosphere.
Oh, I see.
So like really adding
Yeah, we're just adding stuff, right? We're not really taking a whole.
Well, it can't really be.
Um,
There's chemical terraforming considered.
Again, a slightly different issue.
I know.
You bring it up in your chemical terraforming 101 class. So carbon dioxide, methane, H2O. There are other ones that you should probably know of. Nitrous oxide. And CFCs.
I almost said that.
What did you say?
I almost said CFCs, but it is.
Be confident.
Yeah, well, because we like, banned the use of it quite a bit, but it did still be.
Yeah, these were responsible for the ozone destruction.
Yeah.
What is CFC?
Chlorofluorocarbons. So things with carbon chains with chlorine and fluorine attached to them.
Aerosol.
CFCs are mostly artificially created. We use them as so air conditioners use CFCs. You've heard of Freon?
Right.
Right. So that's a CFC. There's also HCFCs, hydrochlorofluorocarbons. Say that 100 times really fast. Give you a good.
Couldn't say it once really simple.
So there's.
That's awesome.
I prefer your honesty. There is a term for these. They're not carcinogen. Not in this form.
Well, they're all gas.
Gases.
They're all gases. Okay. They all have a certain effect that drives climate. Greenhouse gases.
Uh-huh.
Finally, have a soundtrack to this class. It's greenhouse gases. That's where we want to be. So I'm going to add a page here. So greenhouse gases are fairly ubiquitous. They've always been in our atmosphere. Methane is a very common thing. Carbon dioxide is a very common thing, naturally occurring. But they have effects that are both good and bad. And they have various strengths with which they do these things. So let's start with carbon dioxide. So it's just a carbon atom attached to two oxygen atoms. Pretty simple molecule. This is what we call, it's a sort of unity. Unity meaning it is used as the base unit for greenhouse gases. So we compare everything else to carbon dioxide. So like the number 14. Just a number, right? It means 14 ones. One is unity. So if you have the number 6, it just means you have 6 ones.
I see.
So we're going to compare everything to carbon dioxide as unity. So this is going to equal 1 when we talk about greenhouse gas. We have methane. Anyone know how strong methane is compared to carbon dioxide?
24 times.
Yeah, it's around 24, 25. Depends on the time scale you give it. So at 100 years, it's about 25 times stronger. When I say stronger, I'm talking about climate forcing. So warm. So this means it's equal to 25 carbon dioxides, or what we call carbon dioxide equivalents. Has anyone seen that unit? Carbon dioxide equivalent? So this is the base unit for greenhouse gases when we talk about climate forcing. It just means it's worth 25 whatever carbon dioxide.
It's very good.
Yeah, so it's equivalent. So it's not carbon dioxide itself, it's just equivalent to 25 carbon dioxide molecules in terms of density. So if methane will warm, if you have a quantity of methane and it will warm the atmosphere by a degree, it would take 25 times that much gas in carbon dioxide to do the same. Does that make sense? Okay. The next one, nitrous oxide. Anyone know how strong that is? 300 times stronger than carbon. Yeah, there's not much else. So we have a lot of CO2, quite a bit of methane, not much nitrous oxide. The last would be CFCs. These are, depends on which CFC you choose. There's CFC 11, CFC 12. These are 6,000 to about 10,000 times stronger than carbon dioxide. So if you have a tank of CFCs and a tank of carbon dioxide, and you have to open one, open the carbon dioxide. Bury the other one. But this drives something you see all the time. Has anyone seen flaring, especially in gas fields or oil fields? So it's a smokestack that just has a continuous flame coming out. That's actually mandated by the EPA. They have to do that. Because what they have coming out of those stacks is natural gas, methane. So when you talk about natural gas, it's almost entirely methane. And wells leak, and when you do oil extraction, natural gas naturally comes out. But instead of releasing methane directly into the atmosphere, you burn it. So when you combust methane, what do you get? Carbon dioxide. So you decrease your emissions warming effect 25 times by flare. Still maybe a huge waste if you want to use that gas for something, but
That's what I was gonna say, why don't they just turn this way?
Hard to ship.
yeah.
You have to have a pipeline to ship it.
Like that.
It's not like you can stick in the truck and drive it. You have to put in a pipeline for it to transport it.
Really?
And then it has to be produced. It's a pain.
And imagine if I just
Easier to burn.
stuck a pipe out of the
What's the
wall.
worst pain though?
It's just easier to burn.
Well, you mind, like, these companies are thinking in terms of economic pain, and you're thinking in terms of global climate.
Help.
So,
I mean, if it's in North Dakota, that might be one thing, but if it's setting up in a place like Prudhoe Bay, Alaska, that's another. You can't ship. You got to do something so you don't get oil.
it's just, it doesn't pan out. The numbers don't.
Yeah.
Or it's pencil out. That's what it doesn't pencil. So we gave these gases a term. Greenhouse. There's a specific reason we give it this term. Anyone know what it is?
Ozone layer absorbs the sunlight, bounces from the surface back to the ozone, cases energy. Well, all the gases, the gases accelerate the energy of the sun, or perhaps.
I know where you're going. Can help you a little bit. Yeah, there's some internal reflection, there's trapping, absorbing. Yeah, it's all those things.
So I feel like greenhouse effect.
Yeah, that's the name of it. The greenhouse effect. And just a note before this, without the greenhouse effect, we wouldn't be. We'd be dead. Like, think about the Earth as a rock. The atmosphere allows for a greenhouse effect. Any atmosphere causes a greenhouse effect. Causes warming. If you take away the atmosphere, if you take away all the warming, we'd be about 33 degrees centigrade colder. Which means instead of being about 85 today, it would be 0. Actually, no, it would be, well, it's not a 1-to-1 centigrade Fahrenheit. We'd be 32 degrees. It would be snowing. So, 85, snow.
So that means
And that's the hottest
even
time of
colder
year.
than that.
Yeah, winters would be awful. What's it?
That's the hottest time of year.
That's the hottest time. Yeah. We'd be Mars, basically. So the greenhouse effect, this is what keeps us alive. If you think about a greenhouse itself, glass, traps heat inside, that's essentially what our atmosphere is. So when people say greenhouse effect and some climate deniers will be like, that's bullshit, that doesn't exist.
Of course it does.
They don't know what they're thinking about. It's just, greenhouse effect is a natural physical phenomenon.
Negative, in a negative way, but it actually is.
Right, yeah, it just is. It's not a positive or negative thing.
Yeah, we're just got too much heat going on in the greenhouse is all.
Yeah, well, it's getting a little too toasty. So this is the Earth. Well, obviously ground. And we'll say this is the atmosphere. We've got the sun, somehow very close to the Earth, but very small. Let's kind of draw out what's happening just with the energy levels. So we've got light coming in from the sun, hopefully. Hits the top of the atmosphere. What happens?
Some of it is,
You guys can both tell.
Yeah, some of it's reflected back and then some of it makes it.
Right. Okay, so we lose some off the top. It's fine. Some makes it in. Great. So now it's in the atmosphere. What's going to happen?
Clouds.
Okay, there's some clouds. We've got big poofy white clouds.
Highly reflective.
Yep, some will be reflected back out again. What about the rest?
Goes down.
Some of it will go down.
And then also some of that.
Concrete jungle.
Okay, so you've got,
Yeah, there you go.
so some gets absorbed by anything with a dark color, basically. So the darker the color, the more heat or light you absorb, the lighter the color, the more. So this is why glaciers and polar ice cap are especially important. They act as a big mirror. They reflect all this extra back in space. When we melt the glaciers and we melt the polar ice cap, what's the color of water from the sun?
Black. Because it absorbs it all.
Magnifies the heat.
Well, not just magnification, it just absorbs also. I mean, it's the color of that.
Yeah, you stand a swim, I'll find out.
Yeah, for sure. So some of it is absorbed, some of it's reflected. So this is a very surface level understanding of what's happening to the light. There are two other things happening. One is that some light is absorbed in the atmosphere, and the ground radiates heat back up into the atmosphere. So typically what happens is the light coming in, this is high energy light, and we can approximate this as UV or shortwave radiation. The sun's energy is more robust than the ultraviolet shortwave bands, and that's high energy. When it comes in, gets absorbed or reflected, anything that's absorbed is re-radiated as heat energy or kind of low energy radiation. So you've heard of infrared. So on the light spectrum, things like UV and shortwave are high energy end, radio, and infrared on the other end. So the stuff that's coming out is heat or infrared radiation. And this is what keeps us warm. That's the heat. That's what allows us to have seasons in summer.
Where to get the rain.
Drives the carbon cycle, drives the water cycle, drives the nutrient cycles. So when we talk about the greenhouse effect, this is all we're talking about. Just the production of heat by absorbing the sun's energy and re-radiating it as lower long-range radiation. When you talk about climate change, this is the point we're talking about. All this keeps happening. This is not changing. All that stuff on the left. But right here, we're increasing this absorption. We are holding more of this heat energy in the atmosphere. And that's what greenhouse gases do so well. Does that make sense?
And once they're absorbed and trapped, there's no, it just adds.
Yeah, I mean, it'll keep re-radiating and reabsorbing until its quality is reduced. So like if you take a dollar bill and you give it to someone crisp, after about 100 people, it's really wrinkly. So the quality of energy reduces. Yeah, so it's a little bit less than most things, but it stays in the atmosphere for a fairly long time.
So do the greenhouse gases, do they like absorb heat like more readily or like much more than just carbon dioxide?
Right, so that's what sets greenhouse gases apart from sulfur dioxide, oxygen, hydrogen, helium, is that these gases, just because of their physical structure, allow them to absorb certain wavelengths of radiation more easily. And those happen to be in the heat band. And I could explain the physical chemistry of it.
We'll get there.
That would take a couple hours. But yeah, basically they're just.
Gotcha.
And the more complex the molecule typically, the more different wavelengths it can absorb. So that's why CFCs, one reason CFCs are so much
What else?
worse.
Does the moon and its gravitational effect on the Earth have any radiation? I would say.
It drives tides, which partially drive ocean currents. The ocean is our energy store.
Would it also affect the rotation?
Yeah. I mean, it does a tiny bit, but you're talking about like a millennial scale. Like not in the term we're
I think
seeing.
the Earth has different gravitation.
What effect do solar panels themselves have? They'd have to affect somewhat.
They reflect.
You'd be retaining the sunlight coming in.
Yeah, but then you're creating
More
energy.
than what would be reflecting out.
No.
No?
You'd retain about the same amount that would be absorbed anyway. And also, once that energy goes through its cycle, it eventually re-radiates back into space. So, I mean, think about the electricity in this room. That light is just a fraction of what you're seeing in the energy. The rest is heat. This is producing heat, that's producing heat, that's producing heat.
Yeah.
Some of that goes back into space anyway. Yeah, solar panels are such a tiny, 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 tiny fraction of the surface of the Earth. And they produce so little. You're never going to get to the point where solar panels are as
What do you think
much.
the solar panels would help to absorb some of that heat instead of it going back to the atmosphere? Does that make sense?
I mean,
transferring it into like a lesser intense, like in the form of heat or light.
So the thing about heat is that it goes everywhere.
Yeah.
You can't like keep heat from going back into the atmosphere. That's just where it's going to go.
Okay.
But we also radiate into space all the time.
Yeah.
So it's not like it's like if you rub your hands together and create heat, you're warming up the atmosphere.
Yeah.
You're just transferring energy from where it already was somewhere else. So the sunlight coming in, hitting the solar panel, it's doing all kinds of things.
I can understand how today's technology wouldn't mean so much. You know, because you're running, 10% that is solar or less?
Oh, far less.
Across the world. What happens in the future when you're trying to run 80, 90% in solar?
It still wouldn't be much. You could power the
Is that
entire.
going to have a huge effect?
No, it wouldn't even be possible to do.
It's got to throw more heat to the Earth.
No.
itself.
No.
No.
Yeah. I mean, compared to pulling coal out of the ground and burning that.
I'm not comparing it with coal. I'm not going to compare it with anything. I'm
Okay.
just comparing it with myself. Because my brother's got solar panels. He's got a pretty big field out in Victor that, supplies his house and stuff like that. And I'm kind of on board with solar and stuff, but I do know that when I walk behind the solar panels, it's a lot hotter than if I'm standing away from the solar panels.
Okay.
There's a difference in the temperature change underneath the panel than there is away from the panels.
Not really sure why that would be. Solar panels produce so little energy compared to like what this computer is using right now that the effect couldn't possibly be enough to be a noticeable change to the whole atmosphere. You might have a localized effect, but keep in mind we're not creating energy out of nowhere. That sun that hits the solar panels, it's already there.
Right.
Either it hits the solar panels and becomes electricity and goes away, or it hits your roof and becomes heat. Either way, that energy is already there. It's in the system.
It goes from there. I mean, it doesn't just stop right there. You don't absorb every bit of energy that hits a solar panel.
Right.
It's got to go somewhere.
Yeah, but it would go somewhere anyway, with or without a solar panel. You're not changing the energy balance of the Earth by having a solar panel.
So what about the energy transfer, though, if you transfer it into another form of energy? I think maybe the kind of speculation is like perhaps that, like even on a small scale, though, that like sunlight transfers to energy instead of being reflected back. So like even if it's just a small one, it's still doing at least
So
energy transfer that might be positive.
So be careful of assuming that we're getting more energy than we have. So if sunlight hits a solar panel, a certain fraction will be reflected.
Yeah.
A certain fraction will be absorbed as heat in the panel itself.
Yeah.
And a certain fraction will be turned into electricity.
Yeah.
By the way, it's still same amount
Yeah.
of energy.
You haven't made more.
Yeah, no, I wouldn't think you're making more. You're just you're
Yeah,
just
you're
like
converting it to something else.
converting. Exactly.
So if you took a black roof
Mhm.
and you hit it with sunlight,
Yeah.
it's going to create a certain amount of heat.
Yeah.
If you take a solar panel, it's also going to create a certain amount of heat.
Mm-hmm.
But it's going to take a larger fraction and turn it into electricity and actually move it away.
Which is
So
a good thing.
you're just redistributing that energy in a different
Which
way.
is breaking it down a little bit, though, making it less intense, and it's not going into the atmosphere in the form of, like direct reflection.
Yeah.
Like you were saying, as it like goes down the line, it's like less, so that goes into more low energy rather than high.
Right.
The atmosphere.
It's a higher form of energy. Yeah.
I've actually seen heaters made up of buildings.
Okay.
They use a black liner.
Yeah.
Glass front. Sun hits the glass, heats up the air in between. They run a fan through it, goes into the building, and helps heat the building in the wintertime.
Yeah, they're very effective. I mean, anytime you have an energy source like sunlight, you can turn it into
Magnify
something.
it or make it less.
Yeah. So, yeah, those solar heaters are great because they're not pulling energy out of the earth and releasing it, energy that wasn't there before.
Using something that's already coming
Yeah.
anyway.
You're using something that's already in your environment, so you're not actually putting more in. I'm going to stop the video real fast, unless you guys are okay just doing 5 more minutes. Let's just do 5 more minutes.
Yeah.
Sorry, everyone online, if this takes forever to load this video, because it's too long. So I want to go back to something you mentioned earlier, which is the natural cycles of climate change. Climate change is a very natural thing. I mean, you don't have to look further than Mount Sentinel to see the effects of climate change. So those lines on the mountain, those striations, that's from glacial Lake Missoula, which used to be here during the Ice Age. Obviously, we're not in a lake right now, so there's been some climate change. We've had a warming. Before that, we had a cooling. There's a natural cycle to the planet that looks like this. So if you go back 400,000 years, you can see the natural ups and downs of carbon dioxide in the atmosphere, and what follows is a warming period and a cooling period. The issue, what? Oh.
Double what anything ever.
Right. The issue right now is not the climate change, it's the rate of change. So these previous warming periods took tens of thousands of years to happen. And in that time, organisms can adapt genetically. In the pace we've done it, we passed in 1950 the carbon concentrations of the past 400,000 years. We broke that whole record. Within 50 years of that, we broke the record since the Cenozoic period, which is before life existed.
So we're still going up.
Oh, we are going up fast. Yeah. So the graph I had up, this is the famous Keeling Curve. This is what first proved that carbon dioxide was going up. Yeah, Mauna Kea.
Yeah.
Or no, sorry, Mauna Loa. Yeah, big carbon observatory up there. And, prior to the Industrial Revolution, it was pretty flat. We can record that pretty accurately. And then, as development took off, so did carbon. And even Keeling himself said, this probably won't be a noticeable effect in our lifetime. And he was very wrong, unfortunately. you can see the average going up pretty steadily, and it's not only increasing, it's accelerating up. So we haven't tapered off in that. What I want to ask before you go is, what are these up and down motions?
Estimation.
Estimation? That would be a pretty regular periodic estimation.
They found that there is a pattern. I don't know if it's the chart, but it's has to do with the time of year.
Time of year, yeah. So you can see once a year it goes up and down.
Yeah, based on temperature and wind and everything.
It's actually not the wind currents. They're related.
Okay.
Density of the atmosphere changes depending on what time of year.
Not that much. That's true.
Or
But not, you're talking whole tens of parts per million.
in particular to that area that she's gathering.
The location matters. Yeah.
It's the tilt of the year.
Okay, what does the tilt of the earth do?
Well, as the season changed, what was it, precession?
It's like the
So
rise and fall of
pressure,
the ocean.
the atmospheric pressure.
Not the rise and fall of the ocean. That's on a daily. That's on the lunar cycle.
Okay, I give up.
It's the sun.
Bring it on.
Sun.
Coming closer to the sun and further away.
Something to do with our epicycles?
So you two have it. Seasons. It's the season. So if you think about where is most of the land mass?
Northern
Hemisphere.
Hemisphere.
Northern hemisphere. So in the summer, what happens to the northern hemisphere? It warms up. Yeah. Gets green. Our plants
Oh,
grow.
pretty, oh, the plants.
Yeah.
Oh, yeah.
So in the northern winter,
That makes
the
sense.
plants die and release their carbon into the atmosphere.
Yeah.
So it goes up.
Uh-huh.
In the northern summer, all the plants grow again and absorb all that carbon,
There goes.
and it goes down. But you can see it's still going up.
Very minute change.
Wow.
So it's fun. You can see the season. See, history is written. We did not get to energy units and conversions today, so we're going to just start in on that on Tuesday. So come ready to convert your megas and your gigas and your petas and your teras.
Yeah.
All right.
I gotta get that
Bring the
phone
TI-89.
anyway.
Oh, bring that TI-89. Show the world. And those of you online, there's only 2 videos for this class, and we'll start in on again on Tuesday.